welcome everybody, and thank you for joining us. Thank you to the Stormwater Awareness Week organization for inviting us to present on these topics, ion exchange and iron oxide media for heavy metals and emerging contaminants removal. So I'll go ahead. I'm going to go ahead with the agenda that we have prepared for today. The first part is going to be a little bit of introduction of LANXESS and liquid purification technologies. Is the business unit taking care of this separation media that we have? Then we go a little bit on the stormwater runoff challenges and what we are dealing with here. Then we go on some of the solutions that we have in ion exchange resins for selected contaminants. Then we talk a little bit of the bioxide, which is an iron oxide media that we have developed, 20 years ago, and we sell very successfully in arsenic removal. Then we talk about a little bit about the treatment system configuration for IX or ion exchange resins. Then we do more or less the same for bioxide, and then we basically go to key facts and summary of these treatment systems. So with that, let's go with the first part, which is the introduction to LANXESS LPT. LPT we call because it's liquid purification technologies, the business unit taking care of this media. So LANXESS is basically a chemical company. We are a global player in many different markets. As you see, the footprint we have globally is quite large, and we have many production sites in the US, Canada, Mexico, Brazil, Argentina, for Americas, and then our headquarters is in Germany. And we do have production sites there as well in Europe, and some of them are in Asia, India, Singapore, Australia, and even South Africa. So we are very present in many different markets. 8.1 billion sales last year, about 13,000 employees, and basically we spun off from Bayer. We used to be Bayer Chemicals in 2004. We become independent company, and now we again are a global chemical manufacturing player. So with that, let's go with liquid purification technologies. This is one of the business units. We have about 14 business units these days, and one of them is fully focused in ion exchange and separation media. That's why we have the bioxide. So basically, we have more than 1,500 customers around the globe for many different industries like power and microelectronics and drinking water and food. Sugar decolorization is one of the main business for us. And then we are in many different kind of interesting applications like battery, materials purification, and in all of those applications, ion exchange is required because you need to remove impurities or you need to purify any kind of raw material or compound. We have also a Leva Plus, which is a software that you can use in order to design systems for example, softening or demineralization. Now we have a module actually taking care of the food design as well. And we are working in more and more modules to try to help the people to design systems for emerging contaminants as well. I think with that, we can go to the next, which is basically, let's talk about the problem. What is that we are dealing with here? And let's start with a very hot topic that we have been talking about for the last, 5-10 years, which is PFAS. And just to say that PFAS is literally raining these days. And we were using a workshop for drinking water a couple of weeks ago with EPA. They are going to come with a new rule that we are going to talk about at the end of this year. So next year, a lot of people are going to be very busy trying to see what to do with this. But let's talk about a little bit about that, because basically, according to a couple of studies, so it's not safe to drink rainwater anymore, as used to be maybe in the past. rain and also snow melt causes PFAS and other contaminants to leach through the soil and the groundwater to basically contaminate the surface water as well. And depending on some key risk factors is what we need to consider in order to design solutions for that. Like, for example, precipitation rate and what kind of soil type we have, how much of the contaminant is being retained in the soil, and then what kind of specifically PFAS species we are taking care. We are going to see in the rule, they are basically speaking about 6 different species, but there are more than 200 species that are being tested these days all over the place. So it's a very complex problem, and it's something that we have a solution for as well. The runoff from stormwater basically comes from everywhere, and is one of the main sources for surface water contamination, because everything that water can carry on after stormwater, then of course can go to the soil and the groundwater and also the surface water. So you can find from stormwater runoff pesticides, heavy metals, chemicals, plastics, packaging, all kind of stuff. And when we go a little bit more in detail in the TSS, you can find arsenic, copper, mercury, TSS and TDS. I mean, it's not only suspended solids, but also dissolved solids. And most of them, when they are dissolved and they are in solution, you can actually take care of with ion exchange, because these beads, we are going to see a little bit more in detail, can actually retain and selectively and capture and remove very selectively from the contaminated water. So basically, there is an EPA study actually with municipalities in the US, basically counting for 438 different organic compounds coming in stormwater, and 62 of inorganic chemicals can be found in urban stormwater. There are persistent chemicals to be the priority in the treatment of stormwater, and there are several studies about that you can actually talk about. But one of the key words here is emerging pollutants or emerging contaminants, because there are some substances of concern for the soil, for the food, for the health of the humans and the animals and plants, and even the microorganisms. Not only in the water, but then in the soil and even in the air. Like, for example, the PFAS is actually something that can contaminate the air as well. So just to have some kind of idea on that. Sometimes it's very easy, or let's say simple treatment system that can take up these contaminants. Like, for example, if you're in a clean neighborhood and you have these kind of retention ponds, you can actually take care of most of the problems. However, this is not always the case. As we discussed, any stormwater coming from mines or from coal plants or from chemical plants, of course, can have many different kind of contaminants. But even this simple retained pond is something that is risky. As you can see, it's not something that you can actually swim in or fish in, but is something that is really like a dangerous or hazard waste kind of retention site. So that basic system is basically trying to settle down the contaminants in order to provide or to let clean water to run off. But sometimes, like for example, this testing here that we are showing is from Toronto sewage system. You can find things like manganese, for example, exceeding the limit, about 100 ppb when the limit is 50. And then you have phosphorus as well, and then you can have heavy metals like zinc going double above the limit. So this is something very common. This is something that a lot of people are dealing with these days, and we just need to measure and see what is in the contamination. So we say the characterization of the water is the basics to think about any other solution. And then with that, we can think about what to do because, for example, in ion exchange, we have solutions for manganese. Phosphorus is something that you can actually treat with bioxide. And then zinc, there are selective resins that actually can remove the zinc. So there are solutions for every single contaminant. Not all of them, but we have a lot of solutions for that. Since we are a chemical manufacturer, let me talk about a little bit on how we actually sell and what is that, what actually we supply. We supply ion exchange resins. We basically manufacture them. We go from the very raw materials. We produce the beads, as you can see here, that can be heterodispersed, like in this case, or monodispersed, like in this case. And then these resins are actually uh, that we put in several vessels in order to take care of the contaminants. So the bead or the ion exchange is going to have a functional group, usually a type of amine when it's an anion exchange system. Or then we have a polymer matrix, which is usually styrenic most of the times, but we have also acrylic resins. We have some morphology that has to be considered, like gel or macroporous, for example. Then we have also cross-linking, how much of the structure is actually in the bead able to to be, let's say, physically stable over the operation of the ion exchange system, and also how the resin is going to swell and shrink as you load it and regenerate it, depending on the case. That is actually going to determine the operating capacity. I'm talking about the cross-linking still, because the operating capacity is what is actually giving you the capacity of the system in order to take care of the problem. There are different bead sizes. There are some big beads and also small beads. We call them MDS, small monodisperse. And then depending on the functional group, there is kinetics that you need to consider, how quick and how fast and how effectively the contaminant can be absorbed. So this is some of the basic information we have in the data sheet. And here you can see some of the representation, how these beads are actually formed. And this example is for the TP1080W, which is a resin that we sell for PFAS polishing or removal. Again, if you have any question, please feel free to write it down in the chat, and we will take care of that at the end of the presentation. So, as we said, there are some functional groups that we use for make a resin able to do selective removal. For example, we have this VPOC1026 Levatite, which is very, very good, very effective in zinc removal. We have our monoplast, Levatite monoplast TP207, which is usually very, very good for, let's say, transition metals removal, like copper, nickel, but even aluminum could be removed with that. Then we have the TP220 for nickel cobalt separation, and this is something that we sell mostly in battery materials purification. Some anion exchange resins are, for example, TP106 that is used for perchlorate removal, and all of them are being sold here in the U.S. and North America. 272 is something that we also use in separation for battery metals. TP260, very well known in mining and also chloralkali industry. There is one that is very selective for mercury removal. If you have a mercury problem in some kind of mine runoff, this is a resin that you can use. And then there is other that is, for example, the TP107 that is good for chromium removal. So you see, depending on the functional group, then we can expect specifically or selective removal from stormwater. This is another way to show how different resins here in the columns are going to work for different contaminants in the rows. So this is a nice table that you can actually use for quick reference. And this is another one that is a little bit more detailed on what kind of contaminants you have and what kind of resin you can use. And then, of course, all of them are different. And the good news is that we understand very well, of course, each one of them, and we can absolutely provide the necessary support to design the systems to find the right solution for you, depending on what kind of contaminants you are dealing with. But you see, there are many, many different options and problems and challenges that we have a solution for. Um, okay, let's talk about a little bit the PFAS regulation. Coming back to the PFAS problem, this is the norm that is going to be issued by the end of this year, and this is kind of confirmed. EPA is pretty sure they are going to be on time. What I heard a couple of weeks ago is that the draft of the rule is already discussed and is already ready for the administrator review. And this is going to happen in the next 2 months, October and November. And then by December, we will have a final rule for PFAS. And it's going to be basically taking care of these two P4 and PFOS, up to 4 ppt, parts per trillion, or nanograms per liter, which is very, very low. And then there is a group of PFAS contaminants that are going to be, let's say, calculated or measured in a hazard index. And the hazard index is something that we show here in the below picture. Basically, it's a quotient of between the load that you have in the water and also the limit that the EPA wants to keep. For Gen X, PFBS, PFNA, and PFHXS. So the four of them have different limits, but the four of them are going to be grouped in a hazard index that you can actually calculate this way, as we show in the right side of the screen. So if you get less than 1, then you are below the MCL, you are good to go. But if you are above, then you have to have some kind of treatment in order to reduce and get into the below MCL. So that's why we want to bring it up, because it's a very hot topic, and we have a couple of solutions actually for that, both for drinking water and also for waste or industrial water. So questions about that we can take as well. And a couple of slides just to tell you about a couple of solutions we have. The first one is the Levatit TP108DW, which is DW's drinking water. And this is the very high selective removal PFAS resin that we have. Not recommended for regeneration. This is something that is usually used once through. These resins can go for 100, 200, up to 300,000 bed volumes. So it's a very, very high capacity and very selective resin for PFAS, and is approved for drinking water as NSF 61. There is a new product that we just launched a couple months ago, and this is for PFAS as well, but it's regenerable version. So you can actually think about, for example, wastewater or industrial systems where you need to regenerate the resin because the loading is going to be very high. Let's say in the drinking water, you are always in the range below 100 ppt, and you need to get below 10 ppt. But in the industrial cases, you can be in the ppb levels, which is thousands of ppt or thousands of nanograms. And then you need a more robust system with regenerable options, and we have that as well. There's another one, which is Levatit MP62WS. It's a weak basic anion, and it's basically for organic species, including PFAS, but also other problems that you may have in the stormwater runoff. And this is a very regenerable resin, very easy to regenerate as well. It's a macroporous, so the structure is a little bit bigger than these two, so that allows the kinetics to be better, and also the regeneration to be more efficient. Capacity is quite high, about 1.7 equivalents per liter. And yeah, we'll see a couple of examples on those resins as well when you build the systems. There are 3 more, and with this, I stopped talking about ion exchange. Basically, a TP107 that is very used for chromium removal. We sell that here in the US. Can be also used for PFAS, for bulk PFAS removal. It's an acrylic. The other resins we just discussed were styrenic, but this one is particularly interesting because it's another polymeric structure, but which provides a much higher capacity, 2.4 equivalents per liter. So it is NSF certified as well for drinking water, but could be used in wastewater, not a problem. We have the two chelating resins here, TP207 and TP214, and these resins are very, very selective. And in this case, for example, you can see you can remove selectively copper, nickel, zinc, cadmium, lead, even chromium and manganese, and also is used for cobalt removal. Easier regeneration, is macroporous, is good capacity to equivalents per liter, and it's high cross-linking. So it's very, very robust, very resistant, physically stable, and very resistant to oxidizing. The TP214 is a very specific one, which is very effective for mercury removal. We sell that in many, many systems, but also for precious metal capturing. So if you happen to have a runoff or a stormwater that is full of these precious metals, you can recover them with the TP214. We have some information about capacity, but usually this resin is not regenerable. Usually what you do is you capture let's say the mercury and just send it to the landfill or some safe system to dispose the resin. Or you can actually, in the case of precious metals, you can incinerate the resin in order to recover the pure precious metal. And this is usually what people are doing with this resin. Okay, with that, we can stop talking about climate change. Please save your questions. By the end of the presentation, we'll take care of them. Let's talk a little bit about bioxide. Bioxide, EIN20 and EIN30 are industrial versions for, let's say, water treatment. And the main target for this media is arsenic. We sell this resin for arsenic removal globally since many years ago, and we have a big market share on that. But for some contaminants, you can actually use that, like, for example, small concentrations of heavy metals like copper or zinc, and actually phosphorus can be removed with that. Silica is something that we can target with this media as well. What else? Selenium is something that you can remove with this media. Again, in a small, low concentrations, because it's basically a polisher media that we sell in many, many different areas. As I said, it's basically iron oxide. If you think about this media, is basically very similar to granular activated carbon. So whatever you design and you think about how to design with GAC, you can absolutely think in the same way with dioxide. It's very similar in terms of design, and we are going to talk about that as well. As I said, the main target for this is arsenic. So if you happen to have a stormwater runoff with some arsenic contamination, this is a media that you want to put in place. It's the most optimal, the most efficient media out there for arsenic capture. The good news or the good thing about this media is that it's going to capture the arsenic and is going to be so very well held on the structure that you are not going to have any release, any leaching once it's in the landfill. So you can actually store in landfill as a normal, not hazardous waste in the landfill. And this is the very, very huge advantage of this media. But as I said, there are some other contaminants, like, for example, phosphate can be removed with that media as well and can be regenerated. So you can use it for many times, many runs. But silica is something that we also target. At the beginning, we consider this to be a problem, but then with the time, we actually realize that this is actually a highlight of this product, because if you have a silica problem, you can actually take care of that with bioxide. I say here E33, but this E33 is the version for drinking water, but it's going to be exactly the same for wastewater or industrial water. And the good news about that is that it's regenerable. So once it's actually coated by the silica, which is what is going to happen in the particle, that the silica is going to coat, then you can actually regenerate that, removing the silica with caustic soda. And there are a couple of other metals that you can actually target. Again, in small concentrations, low concentrations, you can actually remove them using this media because it's very good absorber. And can we actually use it as a household once through applications, and is being applied for some of the cartridges, for example, for drinking water. But because of that, keep that in mind. If you have a system that is temporary, that is not high concentration, that need to clean up, this media can be a very good solution, effective, easy to handle, easy to design, easy to operate. Okay, then this is more or less what we have for today, but let's talk about how to actually apply those two kind of medias in the solutions for removal. So usually the resins and ion exchange resins are used in lead lag systems. So basically the lead is going to take care of the bulk removal, and then you have a polisher or a lag vessel that is going to make sure you are always under the target that you have. But there are some characteristics of the water that you need to keep in mind. It's not that any water can be treated that way. Usually you have some kind of pre-treatment in order to make the best or the most out of the ion exchange. And of course, we have several studies for specific substances. For example, in this case, it's based for the TP1080W for PFAS. And as I said, you can run very, very long time. For example, this system is in operation for 2 years without changing the resin. And as I said, you can go 130, 150, 200,000 bed volumes with no issue because, again, the capacity and selectivity of this resin is very good for that. This is another example. So you may have a system that is going to remove, let's say, a bulk of the contamination in the first vessel, and then you change the resin in the second, in the lag, in order to take care of something that is more, let's say, difficult to capture. In this case, for example, the MP62WS is going to take care of one part of the problem, and then the second vessel is going to take care of the other part that is not retained by the lead vessel. So that is something that you can actually configure as well. This is, for example, a real example for a chemical plant in Europe. And this case was exactly about PFAS substances like PFBS and PFBA. And you see the characteristics of the water, 20 bed volumes an hour you can run. This is very important, is to say that the empty bed contact time is usually 2 to 3 minutes, not more than that. So it's very, very quick and very high kinetics. And then regeneration can be done as well with caustic soda, as we mentioned. So very interesting system. And then the system can be a little bit more complicated. If you have something that is very heavily contaminated, then you need to make a pre-treatment. You need to put some GSA in place in order to remove organics and some of the PFAS. And I continue talking about PFAS in this system. Then MP62 can take care of this problem. In this case, you see there is a 3 vessels in series system. And after that, you go to a polishing system. And why is that? Why is so complex? Because the concentration is very high. So in order to get to the very high concentration to something that you can discharge, sometimes you require different stages in treatment. And this is something that we can help you to design and to decide what to do in order to best take care of the problem. All right, same kind of 20 cubic meters an hour. The flow rate is here. And this is a system, actual system that we have actually running right now in Australia. But we have systems like that also in the Americas region. Another kind of problem that you can have is natural organic matter. Of course, the runoff from stormwater is going to bring everything that is in the surface, and sometimes organics is a big problem. There is a resin that you can usually recommendation for organics we know is GAC, but if you need to take care of something really specifically and selectively, then this Levatit S5128 is a solution that you can try. Um, you can get up to safe drinking water limits below 5 ppm in natural organic matter, and you can regenerate that resin with a double step with the sodium chloride, and then and sodium sulfate could be also um, used. But this is just an example that could be organics, could be inorganics, could be very low concentration, could be also very high. For example, in this case, we are talking ppm. In the PFAS systems, we were talking ppt. So you can have different ranges depending on what the problem is. So, in general, operational guidelines for ion exchange is basically to keep suspended solids very low, because otherwise they are going to be retained in the column, and then you are going to have not the best efficient operation of the ion exchange. Pressure drop, keep it low. Free chlorine, sometimes free chlorine can actually oxidize the resin, so keep it low as well. Any oxidants, you want to take care not to have a high concentration of them, because otherwise it's going to oxidize the resin. TOC is usually something that we want to keep low as well, less than 1 ppm, because of course can be retained as well by the resin, and then it's going to take some operating capacity from the resin. Oil and greases are not tolerable. You really need to take care of them ahead of time. And heavy metals, of course, keep it down, because otherwise the resin is going to capture them. So it depends on what are you trying to capture. The pre-treatment is something that is very important. 10 to 20 bed volumes an hour, as I said, 2 to 3 minutes. You can actually operate as an empty bed contact time. The vessels could be 8 foot, 12 foot diameter. Cross-sectional linear velocity is 5 minimum meters per hour. The bed depth is going to be 3 feet. We say 1 meter, can go up to 1.5, even up to 2, depending on how big the system is. But keep it minimum 3 feet. Backwash, for example, for some systems is not recommended, but for some systems actually something that we encourage. If you have, for example, TSS coming to the system, you want to remove any small particles from the vessel, or otherwise you are going to have an increased pressure drop. What else? The configuration, as we explained, is usually lead lag, but could be actually merry-go-round, we call them, which is basically three vessels in place. All right, this is all about the configuration of the ion exchange. Let's talk a little bit of the configuration for bioxide. This is very easy, as we discussed. It's something you can handle as you handle the GAC. If you have any system with that and you want to, let's say, remove arsenic very selectively, you can go with a very similar system. The difference is that, for example, the empty-bed contact time in this case is 3 minutes. The empty-bed contact time for GAC usually is between 10 to 20 minutes. So these medias are very much more efficient than GAC for sure. Other than that, the pressure drop, you want to keep it lower. Even, for example, in the ion exchange used to be almost like 2 bars. In this case, we want to keep it below 0.7, because the media is fragile, and then if you put too much pressure, then it's going to crash it. The bed depth in this case is 0.7 to 1 meters, so more or less the same as we discussed for ion exchange. Cross flow velocity is, as understandable, a little bit lower. We talk in ion exchange 5 meter per hour. In this case, is 2.5. Cross flow velocity 20 meters per hour, and the freeboard is usually 50%. This is something that we didn't discuss in the ion exchange, but usually we can have in the ion exchange 80 to 100% freeboard, because when you backwash, if this system is going to be backwashed, then you need to expand the bed very much in order to remove fines. So you probably can go to the 100% in some of the cases. All right. So some of the steps that you need to have before the bioxide start to work is filtering. So we need a pre-treatment to make sure that the water is something that is clean, that you want to remove selectively. For example, in this case, arsenic or any kind of contaminant. For example, in this case, we have arsenic as the main target. Then we have the phosphate, it would be the second target. And then we want to keep an eye on the silica because, as I explained, silica is going to be something that is going to load or to cover or to coat the bioxide. So the three of them are going to be the targets in this case. And because of that, the pre-treatment is very important. A couple of things here is you want to, for example, if you are, if your target, excuse me, if the target is going to be arsenic, the best operation is going to be with arsenic 5. So if you have some indication that you have arsenic 3, you want to oxidize that arsenic with some kind of oxidizer like chlorine, sorry, and make sure the arsenic is going to be in state 5. Also, some pH adjustment. You want to keep the pH in the neutral kind of range. And because of that, you can have a pretreatment with that as well. Then you remove the bioxide when it's exhausted, and actually you can drain it out and dry, and then you dispose it. As we said, whatever we retain is going to be very strongly held, and probably you don't need to label that as as hazardous material. So there are many different configurations that you can actually try, with lead black being the main system that you use. But sometimes you probably can do some kind of bypass. You can actually remove in one vessel and then blend with some non-treated stream if the regulation allowed you to do. And but it's more or less the same as ion exchange. It's lead lag configuration, but you can actually do merry-go-round, which is basically 3 vessels in series. Basically, like one lead bulk removal, then lag just to polish, and then a last one that you probably can put as a extra polisher, let's say. So very similar to ion exchange, but also very similar to GAC, as I mentioned. Depending on what you are removing, how much contaminants you are removing, you can actually play with those configurations in order to make the most of the media and get the longer performance of the media as well. So in summary, it has a long track record. This is something that has been used and is being used for drinking water arsenic removal. It's very easy to install, not different in design from GAC or ion exchange. Basic designs. We can help you actually to design a system if you need to. There are many smart options that you can actually play with, and we have a lot of experience with that, so we can guide you in that kind of selection of what arrangement is the best. Besides arsenic, is something that is used for silica removal, for phosphate removal, and also some other emerging contaminants like heavy metals. This is something that is being used, for example, for remediation projects in Canada are using bioxide to do this kind of treatment for heavy metals. So it's a good option. It's available, and 2 versions, one for drinking water, one for industrial and wastewater. Right. So with that, we cover more or less everything that we wanted to. So let's make a comparison between these two. With the flow rate, composition, and pH, we can actually design a system. If you give us this information, we are very happy to provide a basic design for bioxide. 3 minutes antibed contact time is something that is usually the rule. The pressure drop is less than 0.7 bar. The target concentrations by contaminant, we really need to know in order to see what is the actual operating capacity of the system. We always are very concerned about what is the final disposal, how you are planning to dispose the loaded media, and we are very much concerned about that, depending on the contaminant that you are removing. Is going to be a temporary treatment, or is it going to be a permanent treatment? That's something that is also influencing the design itself, how much media and how big the system has to be. Lead lag is usually the configuration that you use, but could be variations in order to take better advantage of the media. And the freeboard and backwashing is something that we really want to consider, and we absolutely can help with that as well. In the ion exchange side, the flow rate is and the composition, the pH is the information that is enough for us to design a system for you. Basically, to give you a basic design, 2 to 3 minutes anti-wet contact time is something that we usually do. Pressure drop, not more than 2 bar. Otherwise, the resin is going to crash and also break the beads. And we have a lot of customers having issues with pressure drop because when it gets high, and then the beads are going to be broken, and then those broken beads are going to pack more compact, and then it's going to create a lot of problems in the operation. So in that case, it's better to backwash, remove the contaminants, and then if we need to rebed or if we need to top off, you can always do that with the resin. Um, we want to know what is the feed and target concentrations that you are dealing with in order to design a system properly, because the operating capacity actually is something that it depends on the concentration. The higher the concentration in the stream, in the feed, the higher the operation capacity for most of the ion exchange. So we want to know what are you actually facing in terms of concentration and targets. Um, it's different to have a total capacity versus the operating capacity depending on the contaminant. You can have a resin that is very high total capacity, but because the concentration of the contaminant and the selectivity of the contaminant, the operating capacity can be much lower. So we want to keep that in mind, but we always help you to design considering that. Once true can be the systems, for example, PFAS in drinking water, most of the systems are once true, but it can be regenerable. If there is something like copper or heavy metals, most of the time these systems are regenerable, and the resin can run for years and years. We have customers using, for example, I have a customer using for cadmium removal in a specific site, and he has been using the resin for 12 years. No problem. Very, very good performance. Most of the applications are going to be in regenerable systems for 5 to 7 years. And then, of course, the configuration is also lead lag or can be merry-go-round. Freeboard, backwash, and regeneration is something that we help customers to design about. And it's just a figure of it's a chelating resin trying to capture a metal in the middle. You can see it looks like a crab. All right. So in summary, Lanxess is we have more than 80 years in this business for ion exchange. We really are a leader in this market. We know very well the resins, how they operate, how they work better, and we have a lot of experience with the purification and drinking water systems, and also industrial and even complicated waters, many industrial systems. German standards used to say that the quality is something that we really have in the top of our mind. As you see the slogan, most of the slogans of our products in Lanxess in general has the word quality, because we really believe that's the driver for our business. And of course, we constantly train and learn about the um, applications, the products, the new products, new developments, and we really have a very high um, technically expert people that are going to help you with the solutions for any problem. Here are the contacts. This is my name, Wilson Nova Ruiz. I'm based in Pittsburgh. I'm very happy to help many people in this systems design. We have also our technical manager, which is Sendong Liu. He's located in New Jersey. He's the technical manager for Americas. So as you can see, he's very busy supporting people everywhere, but he always has some time for us to talk about design systems. And we have people in Germany. We have other experts here in the US. So we are a very good team to work together, finding solutions. And with that, I think we are pretty much set. Rebecca, I don't know how we handle the questions.
Yeah. So would you like me to read the questions off to you, or would you like to look in the chat?
Yes, please. If you can, let's do this interactive.
Okay, perfect. We've got several questions. So the first one is for CR6 plus. I see the chemicals mentioned are either strong or weak based. Is there an acidic option?
Say it again. What is the problem specifically?
For CR6 plus or hexavalent
Okay,
chromium, I see the chemicals mentioned are either strong or weak based. Is there an acidic option?
Yeah, the resin that we have is the most applied is the TP107 for chromium, and this is an ionic resin. So I'm not sure. In this case, it's a strong base anion, but sometimes, depending on the concentration or depending on the system, actually, for most of the cases, TP107 is going to work, and this is something that we applied in several sites, and it works perfectly. So that is an option that is like top that we have for that problem. I hope that answered the question. If not, let me know.
Perfect. And how do you safely regenerate a PFAS or PFOA or other resin without generating a waste?
That's a good question. There is no option for that because actually, if you are going to regenerate, you need to use an eluant, which in this case, for example, for PFAS is going to be some kind of blend between sodium chloride brine and some kind of alcohol, methanol, or ethanol. And in that specific regeneration process, the waste is going to be there. What happens is that this regeneration is going to generate a concentrate that you can actually dispose. So the good thing about regenerable resins is that the problem you can be reduced very much from, for example, thousands of cubic meters of water containing let's say ppb levels, or let's say higher than 100 ppt levels, to very in the high ppb or even the ppm levels, pp parts per million, which is of course much less volume, much easier to let's say incinerate if you go to that option, which is absolutely valid. And there are many different companies and startups trying to develop new different systems to destroy PFAS. So I guess in this case, the regenerable version is going to create a concentrate that is going to reduce the cost of destruction of the PFAS. I hope that answered the question, but if you regenerate, you are going to have a waste, and then the question is, okay, is this waste good for destruction? In this case, for PFAS, it is.
Okay. And our final question, how common is bacterial contamination from the resin, and how to fix it from happening again?
Good question. Yes, it is possible. We have many customers dealing with that kind of problem. When that happens, we have actually a manual, like a procedure that we can actually share with you in order to clean it up. So basically, it's going to be a cleaner. You run the cleaner through the system. Of course, the problem that you have with that is that usually the disinfectants are oxidizing systems. And if you put an oxidizer, let's say bleach, in an ion exchange system, then the bleach is going to oxidize the functional group of the resin, and then you're going to destroy the resin. And so because of that, you need to be very careful. What do you use in order to clean the contamination? And the question about how to prevent that to happen again is actually very depending on uh, the operation of the system itself. So the regeneration process is something that is going to reduce the microbial contamination, because usually you do that with maybe some kind of acid, high concentration, and you use 1 or 2 molar actually. And or let's say 7.5% hydrochloric acid is something that is going to clean very well a system. But sometimes you need to recondition the system with caustic soda. So that contamination is actually already having some impact in the bacteria contamination that you may have. Usually, bacteria contamination happens because the system is running too slow. So in that case, sometimes backwash and double regeneration is something that you can use in order to uh, eliminate the problem. If this is the problem, then you can actually see how you resize the system in order to run faster. For example, if the resin selectivity allows you to do that. Um, but if this happens, then sometimes it's not something that happens very frequently. Let's say you can have a contamination with bacteria maybe once a year. So that's not really a big problem, because you can always backwash and put some kind of cleaner, non-oxidized or biocide. That there are many options that you can use in order to clean it up and then get back to the normal running. Um, but it's not very common, I have to say. We don't really receive many questions about that, but sometimes happen, and the solution is not very difficult. So we can absolutely guide on that.
Fantastic. Well, thank you so much, Wilson, for your presentation, and thank you everyone
Okay.
for attending. We are so excited for Stormwater Awareness Week, and if you missed any portion of this workshop, it has been recorded. We will be posting it on our website, most likely by the end of the day, but definitely by the end of the week. So feel free to head over to stormwaterawareness.org to see the remainder workshops of the week, and also watch this one again and share it with anyone who's interested. So with that, I'd like to thank Wilson, and thank you everyone for joining us, and we hope to see you at another workshop.